We are Bar-Natan, who will be speaking on Tangles in the pole dance studio. Oh, okay, good. Sorry.
You're making us,
Oh,
you're making us dizzy.
yeah, I'm sorry. Okay. Maybe I'll meet with me later. So, this is my title, and there's more of the title, and maybe just a preliminary definition before I say anything else. So, a pole dance studio is so you fix an integer and a natural number, and for use later, let's fix a field, which is either the rational number or the complex numbers. And the dp is the disk minus p points, and then the pole dance studio, PDSP, is dp cross an interval. So basically, it's a room with p poles removed. You can dance inside that room. And having said that, thank you for inviting me to LesDiablerets. And the talk has a website, and that's the URL. And you can find the handout over there if you wish. And here is the handout in full. I hope everybody is holding a copy. And, I should say that my other passions are work that I do with Roland van der Veen on fancy Lie algebra stuff, which ends up leading to fast, computable, topologically meaningful knot invariants. And I'm really, really, really excited by that, if only because it's contained in polymathematics, so mathematics that can be computed in polynomial time. So, you don't chalk out at 5 or 10, you can compute to 200. I mean, you really can compute. The fact that I'm showing you this is sort of an indication that I'm panicked. Because basically I talked about it in Geneva, in the LesDiablerets sometime before, and in Geneva just 2 months ago. And 2 months ago, I realized I have to quickly come up with a topic here, which is suitable for the topic of this meeting. And unfortunately, I already spoke about things that, are not even properly suitable. So I had to come up with something very, very, very quickly. And fortunately for me, Juji organized a meeting in Sydney with herself and Tamara Hogan and Jessica Liu and Nancy Sheriff and me. And we spent some time learning things, and in particular, reading a paper by Massuyeau and another one by Alekseev and Naef. And to be fair, we didn't really read them. We just tried to understand what's in them, or what we thought was in them. So my talk is about reading these papers without really reading them. So basically, I will tell you about a three-dimensional interpretation of the homomorphic expansions for the Goldman-Turayev Lie algebra. And it's been done already by Massuyeau, but I think it's a very, very hard to penetrate paper. So I hope I will simplify a bit. And I think it was done without acknowledging it by Alekseev and Naef, except they don't acknowledge it. So they write, here is the expansion in terms of the Kniznik-Jamolodchikov connection, without saying, but it also has a three-dimensional interpretation. And it's a brilliant paper, by the way, but to me, it reads like formulas, and it's hard to see what the formulas are saying. So I hope I will be able to at least somewhat fix it. While in Sydney, and knowing what we're talking about, we had fun. So Tamara couldn't come, so we put her picture on the wall and took a picture of herself taking a pole dancing class. So here is Jessica, here's Nancy, here's Yuji, here's myself. And I suppose this sign here says that I should go to the blackboard for a moment. You know, since I have so little content, I hope at least to be entertaining. So I'll tell you a little bit about expansions in general. So so without defining what's an expansion, here are two examples. So there are maps W from the free group with generators uppercase xi into the free associative algebra with generators lowercase xi. And here are two examples. One is the Magnus expansion, and it sends uppercase xi to 1 plus lowercase xi, and then it must send the inverse to the inverse. So that's where the inverse goes. And there is the exponential expansion, which is defined only over the rationals. And it sends xi plus minus 1 to e to the plus of or minus xi. So here's a fun way to think about expansions. So, you know, maybe the standard way to think about expansions is to ask yourself, okay, I told you where does this go? So now I'm looking at x1, x2 squared, x3 inverse, and I'm asking myself, and then let's add another x1 here, and I'm asking myself, where does this go? Okay, so I'm asking myself, where does some short words or product goes to? And it goes to some very, very, very long power series. But I want to look at it in slightly reversed way. So I want to think, suppose I have a very, very, very long word. So x1, x2, x1, very long, x2, x1, maybe some inverted. And I'm asking myself, let's look at the low degree part of the output. So what's the coefficient of 1 in the output? Not interesting, 1. What's the coefficient of xi in the output? So basically, this, let's take the Magnus expansion, the exponential expansion is similar. So this will go to 1 plus lowercase xi. This will go to 1 plus lowercase x1. This will go to 1 plus lowercase x2. This will go again to 1 plus lowercase x1. And then I'm asking myself, how do I get an xi at the output? And the answer is, I can only get a degree 1 result if I take 1 from all of the factors, and except for one factor where I'm allowed to take something of degree 1. So basically, I'm counting in all of these factors how many times I see an xi. And that's the same as counting in this word how many times I see the letter uppercase xi, but I count with multiplicity or with signs. So basically xi to the power 1 counts as a 1, and xi to the power minus 1 counts as a negative 1. So this tells me how many xi's occur. And now let's look at, say, the coefficient of x1, x2 in the answer. And well, basically, I need to look for pairs of factors, one which will contribute the x1 and the other which will contribute the x2. And the one that contributes the x1 should appear before the x2. So I'm basically counting how many times in the original word there is an x1 before an x2. And likewise, if I'm looking for x1, x2, x with a coefficient of x1, x2, x3, I'm counting how many times I can see an x1 and then an x2 and then an x1 again in the word, counted with signs. Okay? So basically, the expansion gives me sort of a statistical profile of the input word. If this is the input word, I get a statistical profile of W. How many times I get various letters and in what order? Okay, and then you can ask yourself, well, there are various operations on words. So one operation is concatenate word. Another operation, so words are really elements of the free group, so you can map from one free group to another, and then it maps words to other words. Another operation is, well, sometimes you have, words are represented, so in 2 dimensions at least, words are represented by, can be represented by loops in a punctured plane. And then there are various operations that we've seen already where you look at double points and smooth at the double points, and then instead of a single word, you get 2 words, roughly speaking. What we're looking for are homomorphic expansions. And homomorphic expansions are expansions that behave well relative to these operations, which roughly speaking means that if you know the statistical profile of the input word, you can tell the statistical profile of the output words. And furthermore, by simple formulas. Okay, so that's, sorry, this is an aside. I told you I want to be entertaining. It's supposed to be. So that's what we're looking for. And the way we do it is by, well, there's something called the Kontsievich integral. And the Kontsievich integral is an expansion for knots. So it does just the same. Namely, so for knots, the output will be in so-called chord diagrams. There's the empty chord diagram, which is not interesting, so I'll suppress it. There is the chord diagram, which looks like a chord. There is a single chord on a circle. There is a chord. There is this chord diagram. There is that chord diagram, and then there are more and more complicated chord diagrams. And the Kontsievich integral, very roughly speaking, counts. So chords correspond to crossings. So this chord diagram will count how many crossings there are counted with signs. This diagram will count how many crossings there are counted with signs, such that their combinatorial appearance in the knot is, so if you trace along the knot, you see the first chords and the seconds and the second and the first. So 1, 2, 2, 1. So meaning if you, how many times can you find pairs of crossings such that if you go along the knot, you go through the first and the second and the second and the first again. This will correspond to how many times on the knot you can find pairs of crossings, so that if you walk through them, so that if you walk along the knot, you pass through these crossings in the order 1, 2, 1, 2, and so on. Okay, so basically what I'm going to tell you is that you can get, and then the Kontsievich integral is a well-known homomorphic expansion for knots, which has very good behavior under various knot operations. And then what I'm going to tell you is that if you know this one, you can figure out that one. Okay? I hope I'm not wasting your time too much. Well, you know, it's only 50 minutes to go, right? Or 40 minutes to go if I am wasting your time, so it's not that bad. Okay, some more formal definitions. So let pi be the same free group that I mentioned over there. And it's also the group of base curves.
I'm not sure from the.
Sure. It's also the group of base paths in the puncture disk minus modulo deformations. Likewise, pi bar will be the framed free group. So it's the formation class of immersions of curves in the plane, modulo deformations of such. Basically, all it means is that this immersion is no longer equivalent, or this curve is no longer equivalent to that curve. Otherwise, it's essentially the same. Let's put an absolute value on a group if we mod out by cyclic equivalence. So basically, pi absolute value means that I look at cyclic words, meaning that if I have a word W and it's preceded by a letter XI, I'm allowed to move the letter XI to the other end. So I just get cycles. And that corresponds to unbased curves in the punctured plane. Let A be the free associative algebra in generators X1 up to XP, and let absolute value of A denote cyclic algebra words. Basically, the only difference is that in the group, or the main difference is that in the group, you're also allowed to have negative powers, and in the algebra, it's just words in the letter XI without negative powers. Okay? And then theorem number 1, which I'm not quite sure where the credits go. So I listed Goldman, Turaev, Massuyeau, Alekseev, Kawazumi, Kuno, and Naef, but I might be missing a few people. Says that, first of all, the cyclic framed words and cyclic algebra words, both of them are Lie algebras. And there is a homomorphic expansion. So a map W from cyclic words to from cyclic group words to cyclic algebra words, which is a morphism of Lie algebras, and satisfies the expansion property, which basically means that the cyclic group word with one letter becomes 1 plus the cyclic algebra word with the corresponding one letter, and then higher degree corrections. Yes.
Yeah, if we're asking about names, there might be many more names, but for sure, big tail.
Okay, noted. And maybe next time I'll add a picture of him as well. Okay. So I of course have to define the Lie algebra structures, the Lie algebra structure, and tell you why there is a homomorphic expansion. So some further definitions. So let K, which I will also call K0, and sometimes K sub-0 up 0, and sometimes K of S, and I'll explain S in a minute, be the space of formal linear combinations of tangles in a pole dance studio. So what's a tangle in a pole dance studio? Here is an example. Except I'm being schematic, so I didn't bother to tell you that the red lines, which are the tangle, sometimes go over and sometimes go under the poles. I just didn't bother to mark which is over and which is under. Okay, I'm just being schematic about the tangles. Okay, now the skeleton of the tangle is basically the list of its components with a little bit of information about each one. So one component goes from bottom to bottom, another component goes from bottom to top, another component goes from is a circle and another component is a circle. So that's the skeleton of this particular tangle. And then if you fix the skeleton in advance and say it is just a circle, so I'm not looking at all tangles, but only knots, then I will put K parentheses S to indicate knots in the pole dance studio with that skeleton, okay? And that was K0 or K0 or K up or K00. And now let me tell you what is K sub T up S. So for that, maybe the best if I'll start with an example. So K5 2 of a circle will consist of pictures as here. This is a tangle in which a circle is tangled, so the skeleton is a single circle, but well, it has 1, 2, 3 ordinary crossings, and I was lazy and I didn't bother to tell you if they're over or under, but they're either way, either one, okay? But it also has special crossings which are denoted by bullets. So 1, 2, 3, 4, 5, of which 2 are strand to strand bullets, and the remaining 3 are strand to pole bullets, right? The vertical lines are the poles, the strand are red. And what this stands for is really a big linear combination of tangles, and it's the linear combinations that you get by replacing every bullet, be it red or black, by a difference of an overcrossing minus an undercrossing. So here you have 5 bullets. So this picture really corresponds to a linear combination of 32 knots. Okay. Now this defines a filtration on the space of knots, or in fact, 2 filtrations on the space of tangles. Namely, the more you increase the lower index, the smaller the space is, because you're looking at more restricted linear combinations that are bigger and bigger. And the bigger the higher index, the strand index, the smaller the space is once again. So this defines a double filtration on the space of knots. Okay. K up slash S or K mod upper S means that you look at the space of all knots and mod out by knots that have, or by the image under this operation of knots that have S strand double point. So S red double points. So here is an example, and that's the most important example. So if you look at K mod 1 of a circle, well, what's that? These are circles in a pole dance studio, except I mod out by circles that have 1 double point. A double point means over minus under. So I'm modding out by saying that by the relation that says that an overcrossing is the same as an undercrossing. So now I'm allowed to flip crossings freely. And if I'm allowed to flip crossings freely for a circle in a pole dance studio, then all that remains, the only information that remains is its projection to the plane, which is a plane curve. Okay, so so if I'm talking about frame tangles, then K mod 1 of a circle is really immersed, is the group of cyclic immersed words of the free group, in the free group, not the group, the set of what I said. And of course, there is a projection from the space of all K of a circle. Well, there's of course a projection to the quotient space to mod out by K1, and that projection is the projection that maps a tangle to its underlying homotopy class. Basically, you project it to the plane. Okay. Next definition. Sorry, I have to make many of those definitions. So calligraphic A is the associated graded of K with respect to the lower filtration, with respect to the total number of double points. So it's the direct sum of KT modulo KT plus 1. And similarly, A up S is the associated graded with respect to the upper filtration. And so we're done here. I think I miswrote here, but that's not terribly interesting because what I really wanted to say, sorry, there's some typos here. That's not very interesting because what I really wanted to say, I wanted to define A upper slash S. So A modulo upper S, and that's just A modulo AS. Where AS is the image of, you know what, without giving a formal definition, it's the associated graded with respect to the lower filtration of the picture above. And it will become clearer in a moment anyway. So now a couple of facts. So fact one is there is the Kontsievich integral. So, I mean, for now, I only told you that A is the associated graded of K. Later, I will identify it with chord diagrams. For now, I don't even need to know that. So I'll just tell you that there is an expansion called the Kontsievich integral. It goes from K to A, and it is compatible with several noteworthy operations. So basically, whenever you have an operation on tangles, you look at its GER. If it's compatible with the filtration, you look at its GER and you get an operation on A, and the Kontsievich integral is compatible with many of these operations, and we'll talk about it when we need it. And then fact number two, or maybe you could say, here is one of those lovely compatibilities of the Kontsievich integral. So it's compatible with the strand-strand Homfly relation. So it descends to a map from not modulo the Homfly relation to chord diagrams modulo the Homfly relation, where the Homfly relation is essentially the defining relation of the Homfly polynomial. So it's the relation which says that an overcrossing, but a red overcrossing, so an overcrossing that involves two strands that does not touch the poles. So an overcrossing like that minus an undercrossing minus the corresponding undercrossing is equal to sum e to the h over 2 minus e to the minus h bar over 2 multiplied by a smoothing. So if you compute z on this and z on that, you get this scalar times z of that, provided you impose the corresponding relation on the associated graded. The corresponding relation on the associated graded is that if you have a chord between two strand lines, then you can replace it by an h bar times a smoothing. And this is the oriented smoothing. So the nice way to draw it is with one strand going up and the other goes down, and then the smoothing looks like a bridge. But if both strands go up, the smoothing look like a swap. Okay, and basically to make everything agree with the gradings, with the filtrations, the degree of h bar should be 1, 1. So this way, the degree on the left is equal to the degree on the right. Okay. And Having said all of that, I can tell you the key points of our reading. So the expansion W, or going from cyclic group words to cyclic algebra words, is really, well, you look at knots mod 1 and also modded by the Humphrey relation. The Humphrey relation actually lives in degree 1. So, or starts in degree 1. So modding out by the Humphrey relation does nothing here. I just wrote it to be nice, okay? So knots mod 1 is just cyclic words, as we said before. And so that the Kontsievich expansion goes into some space of chord diagrams modulo 1. And one of my challenges is to explain why this space is just the space of cyclic words. And furthermore, the claim that this W is homomorphic. Okay, so it respects the Goldman-Turayev Lie by algebra structure on both sides. And here is very schematically the key point, the key reason why this is true. And in fact, I'll show you 4 examples later for how this key point is used. And in each case, you vary something a little bit. But roughly speaking, here's the key point. So suppose I had 2 ways of lifting group words, so paths in the plane, to knots. Most typical example is you lift a word in the plane to a knot by deciding that it is ascending. Another example is to lift a word to a knot by deciding that it is descending. Okay? So suppose you have 2 such ways of lifting plane curves to knots in a pole dance studio. And really what I mean by that is that if you compose lambda I with the projection, you get the identity. Then if you have a curve in the plane, and I define eta of gamma to be one lift minus the other lift. Wait, so I have those 2 lifts. They differ by crossing changes because when projected to the plane, they are the same. So they only differ by crossing changes. So this is a sum. This difference here is a sum of changes where you look at an overcrossing and you replace it by an undercrossing. But the Humphrey relation says that this is equal to, what was it? E to the h bar over 2 minus e to the minus h bar over 2 times a smoothing. But that's a power, this thing here is a power series that begins with h bar plus higher order things. So this difference is divisible by h bar. So take this difference and divide it by h bar and regard it back again in knots mod 1. But knots mod 1, but you see, if I switched a crossing to a smoothing, a 1-component thing becomes a 2-component thing. So I get knots mod 1 with skeleton 2 circles, and that corresponds to a pair of cyclic words. So, so I got an operation. So by having such lambda 0 and lambda 1, I automatically got an operation on plane curves. And now, if Kontsievich likes lambda 0 and lambda 1, maybe, how much time do I have?
15 minutes.
15 minutes. So yeah, so maybe in the interest of time, I will not be terribly specific, but basically likes lambda 0 and lambda 1 means compatible with them in the appropriate way, and it's defined here. So if Kontsievich is compatible with lambda 0 and lambda 1, then there will be algebraic lambda 0 and algebraic lambda 1 acting on the associated graded. You would be able to define their difference divided by h, and it will be in the associated graded space. And then some minor calculation will tell you that the topological operation is compatible with the algebraic operation, which is the homomorphicity of whatever operation we wanted on plane curves. So that's the sketch, that's the schematic. And then perhaps the best thing to do is to go through a few examples. So example number 1 is the stacking product of tangles or knots. So if you have two knots, let's call them D and Z. So yes, Dror and Zhuji. If you have two knots in a pole dance studio, you can just put one on top of the other. Okay. Namely, if you have two curves, so already I'm different from the schematic. In the schematic, I had one curve. Now this one curve became two, but I'm doing the same thing. So I'm defining lambda 0 of gamma 1, gamma 2 to be gamma 1 tilde times gamma 2 tilde, where gamma 1 tilde and gamma 2 tilde are two lifts of the curve gamma 1 and gamma 2, arbitrary lift of the curves gamma 1 and gamma 2 to knots in a pole dance studio. And then I'm defining lambda 1 of gamma 1, gamma 2 to be the two lifts multiplied in the opposite order. So I suppose it would be taking Zhuji down and putting Dror above. And here is another picture of the same thing looked at from above. So the poles are now dots. The two curves are the red curve and the purple curve in this picture. And on the left picture, red is above purple. And in the right picture, purple is above red. And what I'm suggesting is that you would look at the difference of the two. And the difference of to get from one to the other, all you have to do is to flip all the red-purple crossings. So all the crossings between red and purple have to be flipped. Every time you flip a crossing, you use this relation, and it amounts to resmoothing, and then that difference becomes the gold divided by h bar becomes the Goldman bracket. So for example number 1, eta 1 is the Goldman bracket. There is a slight complication here. I think I want to skip it. Okay, next example. If gamma 1 and gamma 2 are two words, but now they're not cyclic words, just words, then I can implement them in the following way. So gamma 1 is this purple curve, gamma 2 is the red curve, and I can put either all of red above all of the interesting part of purple, or the other way around. Both things project to the same two plane curves. And if I take the difference between the two, well, basically I can slide red slowly down to until it's below purple, and then I get the picture on the right. And every time when I slide, occasionally there will be crossing changes. The crossing changes will be determined by the crossings of the two plane curves when you look at them from above, when you look at the pole dance studio from above, like in the picture before. So the difference between these two will be a sum of a sum over crossings of the two curves. And in each summand, you will be replacing the crossing by a smoothing, and that's the so-called double bracket. If you look at it more closely. Here's another example. So this is example number 3. Suppose now you have a single curve, but not a cyclic curve, just a curve in the plane, not a base curve in the plane. I can embedding as an I can realize it in the pole dance studio as an ascending curve or as a descending curve. And here is Nancy demonstrating how to do it. And again, the difference between the two. So basically, think about it. How do I get from here to here? Maybe you can think of it as well, basically, I push this part up while pushing the other part down. I push this side up while pushing the other side down. And as I push, every time that there is a self-intersection in the projection, as I view it from above, I have to resmooth. So I get a sum of resmoothing. And this sum of resmoothing, so from above, my curves look like something like this. And every time I resmooth, every time I resmooth, I replace a picture like I had with a picture like that. And this picture is a combination of a single long curve and a closed component. So the corresponding operation is an operation from words to words, tensor, cyclic words. I think this operation is due to Kuno, but maybe I'm wrong about it.
Maybe not with Nadia.
Well, with Naria, okay. And if you close the first component, you get an operation, and in fact also close the input component, you get an operation from cyclic words to cyclic words, tensor cyclic words. If you anti-symmetrize, this is the Turaev cobracket. If you know the definition of the Turaev cobracket, it's visible. Okay, and then maybe I'll give example number 4. This is the Gwenelian. So Massuyeau as an operation done by considered by Massuyeau. So if you have a word, here are 2 ways of getting or of lifting it into a 2-component tangle, and the two 2-component tangles are the same when projected down. So one way is you make a red copy of the word and a purple copy of the word, and you put purple above red. The other way is you make 2 parallel copies. So you just let red and purple follow the same path up the pole dancing studio. The 2 things when projected to the plane are different, are the same, and therefore the difference of the 2 defines an operation. And the operation is, well, I don't want to even explain it, but it's an operation from words to words, tensor words, and it's a bit messy. But if you massage it a bit, it also becomes the Turaev cobracket. And if I understood Massuyeau's paper correctly, it's based on this operation. Okay. The rest is essentially exercises. So basically, I told you everything, and now you only have to compute the details. So you have to prove lemma 1, you have to prove fact 2, but these are standard 1-9 proofs. You have to determine what is A. I never really said what it is, but again, it's the associated graded of K. So in principle, it's determined. So you don't need any creativity. You just figure out what it is. You need to know what is A/1, and with luck, that will be, and the luck occurs, that will be the space of algebra words, which is what our target space is supposed to be. So especially you have to figure out that A/1 of a circle is cyclic algebra words. You have to explain why Kontsievich likes our lambdas, but in most cases it's really easy. And then you just have to figure out, everything is mechanical. You just have to figure out the corresponding algebraic operations. And then you found 4 homomorphic properties for the Goldman-Hilayev for plane curves, for the expansion for plane curves. So again, how much time do I have? 5 minutes. Okay, so very quickly, here's the proof of fact 2. Here is the proof of lemma 1. Here is the actual definition of the Kontsievich integral. And the Kontsievich integral is valued in a space of chord diagrams. I sketched what they are before, but I sketched them for notes. And if you're looking at Tangles in a pole dance studio, you will also have chords. You'll have chords connecting tangle components to tangle components, so strand to strands, but you'll also have chords connecting strands to the poles. So that's the space. And then there are the usual 4T relations of finite time invariants, but seeing that there are never chords between pole and pole, there are a slightly restricted class of, there are a bit, some 4T relations simply cannot be written. So maybe I'll magnify it a bit. So there are 4T relations between strand to strand chords, and there are 4T relations between a pole and 2 strands, and they're written here. There are no 4T relations between 2 poles and a strand, because you simply cannot write them if you're not allowed pole-to-pole chords. There are some gradings in this matter, and perhaps I will skip the comments, but only tell you that only explain what is A/1. So A/1 is A, so the space of chord diagrams, modulo the space of chord diagrams that have at least one strand-to-strand chord. But this means that in the 4T relation, one of the sides has a strand-to-strand chord, but I'm modding out by these. So what I'm left with is that if you have 2 strand-to-pole chords, then you can flip the order in which they connect to the pole. But that means that if you have say you're looking at A mod 1 of a circle, then that's a circle with chords connecting to the poles. But the order in which they connect to the poles doesn't matter. So the only thing the information that remains is you run around the circle and you read out which pole do you connect to. So here you connect first to X, then to X, then to Y, then to X, then to Y, then to Y, then to X. So this corresponds to the cyclic chord X, X, Y, X, Y, Y, X. And that's the isomorphism of A/1 with cyclic algebra words. So now my expansion has the right target space. And a further observation is that if you mod out by the Homfley relation, A/2, then the commutator of 2, so basically if you want to switch the order of 2 chords that end at a pole, you can replace it by a commutator that happens on the strand. Now, here I have one strand-to-strand chord, and that by the Home-Free relation can be smoothed. So basically, this becomes a difference of two pictures like this, and people who know the Goldman-Turaev bracket should recognize the like little correction you make to the cyclic words at the smoothing. This is exactly the little correction you make. And I wish I had more time, but here is the analysis of eta 1 algebraic, and it comes out what you expect. Here is analysis modulus omlive of eta 3 algebraic, which is the thing that leads to the Turaev co-bracket, and it leads to the Turaev co-bracket as it should. And therefore, the Turaev co-bracket, or therefore our expansion W is homomorphic relative to the Turaev co-bracket. And except this is ignoring a few complications. Again, seeing that I'm out of time, here is how you unignore the complications. But again, I'm only showing it without explaining. But maybe I should spend some time telling you that there is homework. Okay, so the homework is, well, is there more than examples 1 through 4? I think it's an obvious question. So you see, I told you what are the Lie by algebra operations from our perspectives. They're kind of secondary operations for the Tangle operations. The differences of Tangle operations where these are mostly trivial. But there should be a way to derive the Lie by algebra axioms from this perspective. So, the Jacobi identity is obvious because the bracket is a commutator in our picture. But I don't know how to derive the other axioms. It shouldn't be hard. I'm just new to the subject, so I haven't tried it very hard. Homework piece number 3, what happens if you don't mod out by Home-Free PT? That's analog to the question I asked Kai. I think I asked you, right? So if instead of smoothing, you just keep double points as singularities and consider knots with sort of 2 lobes, you get potentially stronger properties. What are they? So in this language, can you recover the Kashiwara-Verne conjecture or Kashiwara-Verne statement? Because Alekseev, Puno, Kawazumi, and Naef recover it in a different language. So can we just translate it to our language? How is all of this related to W knots? So Zhuji and I have sort of a whole story about W knots and about 2-dimensional knots in R4 and the Kashiwara-Verne. So this must be related. Maybe I'll skip number 7. I should also say that there is an alternative expansion, the Habiro-Massuyeau expansion for links in handle bodies, right? The pole dancing studio is really a handle body. So it's the same links, but they use a different filtration. So their story is actually different, and I don't know the relationship. And maybe the last question is for Benjamin, who unfortunately left about 5 minutes ago. And the question is, can he jump? Can he dance can he pole dance on a surface, a punctured surface cross an interval, rather than a punctured disc cross an interval? And thanks many people, and especially thanks all of you for bearing with me and listening and allowing me to go 3 minutes and 40 seconds over time. I forgot I had a timer. I didn't have to ask.
Thanks a lot. I maybe have a short question about one of your questions. So like one could imagine or one could speculate that if you diagnose K/1 or whatever K/2 or then you will create further operations a little bit like maybe, I don't know, an analogy to what Natalie was speaking in the morning with more like more of the crossings and as you were explaining, right? Not just one crossing somewhere, but maybe many crossings. Is it clear that something like that should work or that there are some obstructions that one should foresee or what?
I don't foresee obstructions. On the other hand, so basically, there are many more operations you can do on plane curves. And it is possible that many more of them are well behaved with respect to this expansion. I don't know. I mean, it's possible that all of these operations are compositions of the operations I've already introduced. I have no clue.
Okay, so maybe it's a good time. Thanks again, Dror.
Thanks our organizers for inviting us here.
Thanks a lot. Recording maybe the very short word of advertising. In fact, this conference is organized by this conference center, the Swiss Research Station, and at some point, Thomas and I